lecture for just a bit. Is that all right with you guys? I have to record this anyway. I'm going to do a proper lecture on this anyhow. All right, so the physical properties of minerals that we use to identify them include hardness, or the ability to scratch a mineral, tenacity, which is how the mineral actually deforms when broken, habit, which is how the mineral grows, the shape it takes when it grows, cleavage, which I just explained to you, how it actually breaks if there is a specific direction in the atomic structure that will allow it to break. Fracturing, however, is when a mineral doesn't have a cleavage plane, or if it does have a cleavage plane but breaks in a different direction than the cleavage plane. And you can have uneven, hackly, fibrous. There are different words to describe how the fracture looks, because fracturing is different than cleavage. Cleavage has to do, again, with the atomic structure of the mineral. Make sense so far? Is this going to be on the test? Smithereens. All right. Luster is how the mineral actually reflects, transmits, or absorbs light, which is very different than the color. Color is essential in some cases. Color can help. Hematite is, well, pretty distinctive. That being said, there are several minerals that look very much like hematite, like goethite is one, for example. So color is not the best use. It's probably one of the last things you want to use to identify a mineral. I don't know. That's one of the first things. People are like, oh, pretty purple. It's amethyst. Not always. Lepidolite's also purple. There are a lot of minerals. There's 5,400 plus minerals. Color's a terrible diagnostic. And what about if somebody's colorblind? I've trained geologists that are colorblind before. You do need to understand other properties. I'm getting there, Fragile. We actually use what's called specific gravity more so than density. Although we do use density, specific gravity isn't it's a unitless number. It's actually the weight of the thing relative to the same weight of the ratio to the same volume of water. So specific gravity is a little different in that case, and it's measured a little bit differently. But we call that heft, and we can do heft tests by, well, if you were to grab a piece of galena, which has I think a specific gravity of 7.6 or something, it's lead sulfur. It's a lead sulfide. Compare that to I don't know. Too big. Fuck it, this will work. Compare that to this calcite here. Right? They're about the same size, right? So you want to compare two minerals that are roughly the same size, right? And then you can get an idea of which one is actually denser than the other. And that's an important thing to know. You're like, oh man, this has obviously got a higher specific gravity or is much denser than this mineral. So you can put even if you don't understand or you can't measure the numbers, and I don't teach that. We don't teach how to exactly get the exact number of the specific gravity. That's some high level grad. All right. We don't do that in an undergrad. But just these two alone, you can tell that this one is much heavier than this one, despite the fact that they're very, very similar in size. They almost take the same volume. So you could put, wow, this is metallic. You can see the light reflecting off of it in a very metallic way, which is considered luster. So it's metallic and it's dense. Those are two very distinguishable properties about this mineral called galena. Hematite tends to have heavier than minerals, yes. Hematite is a denser mineral, yes. And I'm trying to think of the minerals that actually look really similar to it, but there are a few. God, these lights actually, massive volume. For density, yeah, but we don't measure it in class. Density does equal mass over volume, that is correct. Open cage. But for whatever reason, it's listed in specific gravity more so than density, and I don't really have an answer as to why, but sometimes you see both density and specific gravity listed.
Fresh meat.
That's actually really, really good good point, Pelin. If the specific gravity of a mineral is less than 1, it will float. That's it's the ratio to it's the ratio to the volume of water, and I don't know how else to explain it. I'm gonna leave that one there actually for displaying metallic luster. Streak I talked about. It's how the mineral is either going to be broken up, pulverized, or literally streaked along a plate. Yeah, unless it's porous. You can have porous, well, you're gonna get more porosity with a rock than you are with a mineral. Sandstone especially, or even, yes, sedimentary rocks especially, typically. The crystal classes, there are 6. I'm not gonna go into detail of those today. But I want to go over them at some point for you guys. It's unitless. Specific gravity is unitless, whereas density is not. Density does have units. Other things that you can use that are actually very, very useful are fluorescents. We don't usually keep UVs just chilling out in 100 level classes, but it is a thing that works. Fluorite is very fluorescent. As are many other minerals. Willemite is a bright fluorescent mineral that looks fucking gorgeous under UV, especially under shortwave UV. Magnetism, of course, is important because certain minerals are magnetic, like magnetite and sometimes hematite. Hematite can be slightly magnetic. Effervescence, that's when you can use hydrochloric acid. Again, it's dilute, it's 5 to 10%, and you could drop it on a mineral, and it actually reacts with carbonate specifically. And it dissolves the carbonate, which is why it bubbles. And I'm going to show you that. I'm actually going to scratch a bunch of one of the minerals and let it go to town bubbling so you can actually see that this time. I'm trying to think what else. All right. I'm going to move on to hardness. The most hardness scale is unitless. It's a 10-point scale. Each point is represented by a mineral. Materials of equal hardness with difficulty can scratch one another. Important to test fresh surface due to alteration and weathering. This is really, really important. Let's say you are out and about and you find a mineral. Like Nini did. She actually sent this one to me. And she's like, hey, what the heck is this? Right? Well, it's actually really important if you were to break that mineral open to get a fresh surface. Because you can actually have coatings of other minerals on it that can be deceiving as to what that mineral actually is. So typically what you do is you would collect a lot of the sample, so you don't mind pulverizing it, you don't mind breaking it open, maybe keep some that's pretty that you don't have to break. But it's important because the surface not only can be coated in other minerals, but it can slightly alter due to chemical weathering, for example. Does that make sense so far? Yes, the acid is dilute. It would be CO2. I would release CO2 in the case of the carbonates fragile. And yeah, it's dilute. It's 5 to 10%, like I've been saying. So far, so good, guys. And sulfates, I don't think it would react with sulfates, to be honest. Not at 5 to 10%. I want to know now, because that's the way we determine if it's a carbonate is using it's CO2. I don't think it's not gonna provide that effervescence anyway. I mean, oh yeah. Okay, so if it was actually 100% HCl in that case, no, I would not put it on anything with toxins in it. It's a good point, but no, because it is a 5 to 10% dilute, it's not going to do anything to anything other than carbonates. Exactly. So no, we don't hand out anything but dilute HCl ever. I've never worked in a department that we've handed out anything but dilute HCl. Oh my God, you can see the birefringence in that calcite. Do you see that rainbow? Do you see that rainbow, Fragile? In this one right here. Do you see it? Do you see it? Do you see the colors repeating? Oh, that's so cool. God, calcite is in such a high order of magnitude on the birefringent spectrum. It's insane. It's actually 4, not 5. Kyanite can be a hardness of 4 or 7 on different planes. And we'll go over the Vickers hardness. This is crystal lattice. Oh, this is an example of how hardness can be different on different directions. This example is, oh, maybe it is 5 and not 4. Maybe the hardness is 5. Can magnetism be a means of identification? Absolutely. Certain minerals are very specifically magnetic. Besides magnetite and hematite, I don't really remember what common minerals are magnetic off the top of my head. What minerals are magnetic? All right, look at this. Chromite, columbite, ferberite, franklinite, ilmenite. Oh, I did know about ilmenite. Magnetite, obviously, and babingtonite. But here's the thing. A lot of them are weakly magnetic, so it's kind of hard to tell. Iron minerals, too, fragile. Magnetite has iron in it, no nickel. Iron, nickel, and cobalt. I don't remember off the top of my head, and I probably should know, but these are weakly magnetic. Oh, ilmenite only weakly when heated. And iron, nickel, attracted to magnets. Magnetite is strongly. I don't know what this is. Oh, platinum's weakly. Pyrrhotite. But it's inconsistent. Siderite. Weakly when heated. I have some siderite, but I've never heard it to be magnetic, only because it's, I don't know. Just, although it's not a very common mineral that we use in mineralogy or anything. It's just one that I used a lot during my master's. You exclusively have useless knowledge. I don't think it sounds useless to me. You know, every single element, but no jack shit about their properties. I can't remember every single element, but I remember a lot of them just because of the SEM stuff that I used. Like, I don't remember a lot of the... anything at the very bottom of the periodic table. Like the bigger elements. Things that aren't as commonly in minerals, basically. That's actually my streak plate, or my glass plate that I use to show hardness of minerals. So this is the Vickers hardness versus the Mohs hardness. So first, I should switch this. So this is the Mohs hardness scale, and it's unitless, but it does give you an idea of what different things are and their hardnesses, so that you can use them to test. Each of the numbers correlates with a very specific mineral. Diamond being 10, corundum being 9. Corundum is rubies and sapphires. Okay? And that's a 9. Topaz is 8. Yeah, Bo! Quartz is 7. And quartz is very, very, very abundant. So you can actually use it to test other mineral hardnesses if you wanted to. Orthoclase / plagioclase is usually about a 6. And I have a ton of that. Apatite is a 5. Fluorite is 4, calcite 3, gypsum 2, talc 1. And then, of course, your fingernails about 2.5, copper penny 3.5, knife or a glass plate. I don't use knives because different knives have different alloys. I use a glass plate, which is 5.5. Steel nail is 6.5, or apparently if you get a masonry drill bit, it's an 8.5, but I've never had the opportunity to have that. This is the mineral test kit that I have. And it's very, very useful because you have a mineral that has 1 through 10. You don't get diamond in there, but you get through corundum. Okay, yeah, you're not going to have to worry about diamond, I'm sure. It includes the names of the minerals that are in here. You can also get a hardness pick set, which I want, but I can't afford. Someday I will. Oh, I need a new hand lens. You can get streak plates. You get geologist tool. You get field books. Ooh, topo maps. Wall maps! I don't like tumbled stones because they just are dumb. Fluorescent kits, rock kits, mineral kits, gem mineral kits, which I don't really care as much about. Fossil kits, which is neat. I could potentially teach historical if I did that. But hand lenses are only $20 on this site. I have that little guy. I've never had this brand of hand lens, but I've always done conferences and stuff, and they give you them sometimes at the end of the presentations. Let's see here. Streak plates. You can get 3 for $3.99 or 10 for $9.99. The white are sold out. White are always the ones that people use the most. But black are nice because many minerals actually have a white streak, and well, you can't see it. So on a white streak plate, you either have to say streakless / white streak ? So it's kind of annoying, and they don't ever offer these in the classroom, which I don't understand why. Lanyard. Do some minerals react to UV? Yes. Some actually bleach in sunlight naturally, and then others fluoresce in UV. Yes, fluorescence does play a role in identification. Typically, we don't use them in classrooms because I think maybe it has to do with people not wearing eyewear. I don't know, but I've never been in a class where we've actually used fluorescence to ID minerals, except to mention that it is a property, and it has to do with electrons jumping out of their shell into an outer shell, and then they quickly bounce back, emitting the energy as a different color of light. And it's really quite fascinating. The fluorescence color, this is actually pretty interesting. I don't have this kit, but I do have a small group of minerals that are fluorescent. So you can buy that if you want to. It's kind of fun. Rock hammers, of course, I've showed you guys these in the field. Hand lenses are what I don't know why. I've never used a gold pan in my life, except as a kid to have funsies. Geologic field books are great in the field because they're waterproof. So yeah, you can't really erase in them because they just make a mess, but they're really great in the field. Try to see here. So that's the fluorescent stuff. That's the hand lenses if you want those. All right, that's geology.com is one of the areas you can find a good amount of information. But I think we've exhausted the Mohs hardness scale. The vigorous hardness scale is actually the one with a number. We can measure a hardness of every mineral. And you can see that for the most part, these minerals are all on the Mohs hardness scale. And so they wanted to show you relative to each other how hard they actually are. You can see that the from talc to corundum, it's not linear, but it's kind of almost linear. Yeah, it's almost logarithmic. Yeah, it's almost logarithmic, but it's basically the big takeaway here is that these are pretty good in terms of being consistently hard from one another. And then you get to diamond, and it shoots all the way up. So diamond is insanely harder than these other minerals. But what does hardness mean, guys? I told you what it means. What does it mean? Does it mean how easy it is to break the mineral? Is that what it means? Yes, what it takes to scratch it. Exactly, Dini. The mineral scratches. Yep. No. In this case, no, Ina Beta. In geology, hardness has to do with how easy it is to, well, scratch or pulverize that mineral. That being said, it doesn't have anything to do with how it breaks. The way it breaks, the deformation, that's called tenacity, which you can have brittle tenacity. Diamond is exceptionally brittle. So you can try to scratch the surface and you may not be able to, right? But if you take a hammer to it, it's going to shatter. Does that make sense to you guys? Yeah, diamond is very brittle. So is quartz. A lot of minerals are very brittle, but you can also have elastic minerals and you can have plastic minerals. And those are two different ways. Elastic means you can deform a mineral and it will bend back into its original shape. Plastic, however, means if you bend the thing, it won't return to its original shape unless you bend it back. It'll retain the shape that you deform it into to a certain extent. Eventually it'll snap, depending on the material. Does that make sense? Elasticity relates to tenacity. Hardness is how easy it is to scratch the mineral itself, to abrade it.